In this lecture, we examine closely the formal definition of the derivative, and then we attempt to find a pattern for computing the derivative of powers of x. The derivative of the function f of x at a particular value x equals a is the IRC, the instantaneous rate of change, or the slope of the function at this x value. Again, the derivative is the same as the IRC, is the same as the slope. The derivative of a function at x equals a is the IRC there. It is abbreviated f prime of the value a, and it's defined this way as the limit of slopes. F prime is the limit as the change in x, delta x, gets close to 0 of the rise over the run of the function. F of a plus delta x minus f of x, those are y values in the numerator, divided by a plus delta x minus a, those are x values in the denominator. This ratio is a slope. We're taking the limit of the slopes as delta x goes to 0. And the denominator, a plus delta x minus a, is just delta x. So here's a slightly simpler version of the derivative. It's the limit of delta x goes to 0 of these two y values in the numerator divided by delta x. This is the slope of the tangent line at the point a, f of a. It's the limit of the slope of the secant lines through p. It is the limit of the average rates of change. The notation delta x is common for describing the change in x. Another common letter to use in this definition is h. So in some textbooks, you'll replace delta x by h, and so the limit looks like this. The derivative is the limit of rise over run, where the denominator is h. This is the limit as h goes to 0. An equivalent definition given in the OpenStax textbook is that f prime of a is the limit of f of x minus f of a in the numerator, that's the rise, divided by x minus a, the run, as the x value goes to a. Standard notation for the derivative is dy over dx is the limit of the slope. dy over dx is intended to remind us that the derivative is a slope. It's a rate of change, a ratio of change in y over change in x. All of these versions of the derivative definition say the same thing, and you should get used to seeing these. The derivative at a point is the IRC, or the slope of the tangent line, and by definition, it's the limit of the slope of lines running through P and nearby points, that is, the average rate of change, or the slopes of secant lines, as those other points approach P. For example, let's use the definition of the derivative to compute the derivative of the function f of x equals x to the fourth at an arbitrary point. Here's how we do it. Again, we're using the definition. So f prime of a will be the limit as h goes to 0 of this rise over run. In our case, my function is the fourth power function. So f of a plus h is a plus h to the fourth power. And f of a is a to the fourth. So we have a plus h to the fourth minus a to the fourth on top, and the denominator is h. Now, a plus h to the fourth power can be expanded into this expression. A to the fourth plus 4a cubed h plus 6a squared h squared plus 4a h cubed plus h to the fourth. We will talk more about that expansion in a different lecture. It's based on Pascal's triangle and can be done very rapidly. You should get used to doing this a few times. In this case, I can factor, once the a to the fourths have canceled, I can factor an h out of the numerator. I have an h in the denominator, and we have algebraically been able then to simplify my expression this way so that the denominator goes to 0. When we were talking about limits and the algebraic simplification of limits, it was important that we attempted to get rid of a 0 in the denominator. We've done that here. Now once I let h go to 0, anything with an h in it will disappear, and there's my answer. What we've just shown is that the derivative of the function f of x equals x to the fourth at x equals a is 4a cubed. Let's do another problem. Suppose instead we have the function f of x equals 1 over x. Again, write out the definition of the derivative. This is something that you should be comfortable with and be willing to use. We will, for the next few weeks, write out the derivative by this definition. The derivative at a is the limit of a ratio. On the top, f of a plus h minus f of a is rise. In the denominator, h is run, the change in x. Now in this case, what is my function? My function is 1 over x, so f of a plus h is 1 over a plus h. And f of a is 1 over a. So the numerator becomes 1 over a plus h minus 1 over a. The denominator is unchanged. This is an ugly fraction. We have fractions in the numerator. The way to handle that is to simplify the numerator by getting a common denominator of those things in the numerator. So 1 over a plus h minus 1 over a has a common denominator of a times a plus h. So in my next step, I can change the numerator in this way and then simplify the numerator, and I finally get a fraction in which the numerator is a fraction, but it has a minus h. There's a minus h in the numerator of the numerator, and the whole thing is divided by h. Those two h's cancel out, and I'm now looking at a limit of minus 1 over a times a plus h as h goes to 0. As h goes to 0, this simplifies to minus 1 over a squared. So if my function is 1 over x, the derivative at a point a is minus 1 over a squared. One more example, another slightly complicated one. Let's look at the square root function and ask for the derivative. By the limit, here's my definition. I've decided this time, instead of using a, I'm going to use x naught, just to use different notation. Should not be a problem. There's my definition. Now, what is f of x? It's the square root function. So what is x naught plus h? F of x naught plus h is the square root of x naught plus h. And what is f of x naught? It's the square root of x naught. So the numerator becomes this expression, and we have a denominator of h. We need to simplify this in some way. How do we do that? Notice that the numerator involves square roots and a minus sign, so we can multiply top and bottom by the conjugate. In order to simplify this expression and eventually get rid of that h in the denominator, we want to multiply numerator and denominator by the conjugate, by that thing, and so we'll do that in this next step. There, I've multiplied numerator and the denominator by the conjugate, but the numerator can now be simplified because the numerator is this expression with square roots with a minus sign, followed by expression with square roots with a plus sign. And if you understand the idea of conjugate, we're going to get the difference of squares formula. And so the numerator becomes, the square roots go away in the numerator. We have x naught plus h minus x naught. And that simplifies to h. But what is our goal here? Our goal is to get rid of h's in the denominator. Well, now we have an h in the denominator and in the numerator, and those two will cancel. And so we get this expression. Now we're taking the limit as h goes to 0, and this expression, can we just substitute h equals 0 and see what happens? Yes, we can. If we substitute h equals 0, we end up having 2 square roots in the denominator, and so my answer is 1 over 2 square root of x naught. So there's the derivative of the square root function at an arbitrary point where the x value is x naught. We've shown that the derivative of the square root function at x naught is this expression, or if you want to go back and use a's instead, the derivative at a is 1 over 2 square root of a. In exponential notation, this means that the derivative of the square root function is 1/2 x to the minus 1/2. Turns out there's a pattern here, and we'll talk about that in the next lecture. Earlier work showed that the derivative of the x to the 4th power was 4 times my x variable cubed. The derivative of the 1 over x was, this is an error, the derivative of 1 over x was minus 1 over a squared. The derivative of 1 over x was f prime of a equals minus 1 over a squared. I'll have to correct that. In exponential notation, this was minus x to the minus 2. If I summarize all of these in a table, the derivative, so I'm going to put in this table on the left column the original function, and the second column the derivative at a particular x value. If I want the instantaneous rate of change of the function x to the 4th, then at a particular x value it's 4x cubed. If I want the instantaneous rate of change of the square root function x to the 1/2 at a particular x value, it's 1/2 x to the minus 1/2. If I want the instantaneous rate of change of 1 over x, or x to the minus 1, at a particular x value, it's minus x to the minus 2. There's a pattern occurring here. We'll call it the power rule that we'll discuss in the next lecture.